Today's workshop will focus on molecular geometry, hybridization, and polarity. So the first question here, we have these three molecules drawn as Lewis structures, and what we're asked to do is identify the molecular geometry as well as the hybridization state for each carbon. So looking at the first one here, we have a CH3 with a negative charge. So let's draw that out. We have a carbon. We have three hydrogens. And we have a lone pair giving carbon a negative charge. So we have four things connected to that carbon. Those four things are going to spread out in the shape of a tetrahedron. However, remember, when we consider molecular geometry, we ignore the lone pairs. We treat them as if they were invisible. So the molecular geometry of the CH3, similar to NH3, ammonia, would be trigonal pyramidal. Okay. And what about the hybridization state? The hybridization state, this carbon is connected to four things. For me, that's the easiest way to consider hybridization state, is consider the number of things that the atom in question is connected to. So this carbon is connected to four different things. We have three hydrogens and a lone pair spread out in the shape of a tetrahedron, which gives this sp3 hybridization. Okay. For the second question here, we have HCN, hydrogen cyanide. We have a central carbon that's triple bonded to nitrogen and single bonded to a hydrogen. So what's the molecular geometry here? Well, the molecule's already drawn out. We have a triple bond, carbon with a triple bond and a single bond. So this central carbon is connected to two things. Those two things will spread out as much as possible. Remember Vesper theory. Substituents around an atom will repel each other. So if we have two things connected to this carbon, that means they'll spread out in a straight line, 180 degrees apart. So this would be linear geometry. And what about the hybridization state of each carbon? So this just has the one central carbon. The central carbon is only connected to two things. Alternatively, you could remember that if carbon has a triple bond, it is sp hybridized. Okay. And then for the third one here, this one might be a little bit tricky for you, but we have three different carbons. Well, the two carbons on the ends are similar, but we have three carbons in this molecule. Let's first consider these two carbons on the ends. They are both double bonded. Let's draw it here. They both have two bonds to hydrogen and then a double bond. Okay. So I'm just going to draw, this is one annotation you might see. It's a squiggly line perpendicular to a bond. And this simply means it's connected to something. You know, we're just drawing this part of the molecule. When you see a squiggly line like that, it just means it's connected to something. So we're just focusing on this carbon right here, CH2 with a double bond. We have one on the left side, one on the right side. This carbon has three things connected to it. How do three things spread out around a sphere as evenly as possible? Well, they become coplanar and they spread out 120 degrees. So they're all in the same plane, 120 degrees apart, which would be trigonal planar. Trigonal planar. Okay. And then what about the hybridization state? Well, this carbon is connected to three different things. It's connected to a hydrogen, and then over here a carbon, double bonded to a carbon there. So it has three different substituents. You could alternatively remember that carbon with a double bond and two single bonds is sp2 hybridized. So there's an example of something that's sp2 hybridized. So both carbons on the ends are sp2, but what about this carbon in the middle? Let's draw this here. We have a carbon double bonded to a carbon on both sides, okay? So just focusing on this central carbon here, well, I'll draw these hydrogens here just for clarity. So just considering the central carbon here, let's first consider the molecular geometry. This central carbon is connected to two things. Two things spreading out as much as possible would give you a linear geometry, right? They'll spread out 180 degrees apart from each other around this central carbon atom in a straight line. And what about the hybridization state? Think about this one for a second. You might want to pause the video here and think about the hybridization state. So the hybridization state here would be sp. sp. Now, we did learn before, I'll draw up here, when we have a carbon with single bonds, that's sp3. If we have a carbon with a double bond, it's sp2. And if we have a carbon with a triple bond, it's sp. But a better way to think about it, this looks nice visually, but for this problem in particular, a better way to think about it is if you have one extra pi bond, which I'll draw in light blue here, if you have one extra pi, if you have a pi bond, that means you have an sp2 hybridized carbon. Remember, because one of those p orbitals is responsible for this pi bond, so it's sp2 instead of sp3. And if you have two pi bonds, in the case of a triple bond, that means you have two of those three p orbitals responsible for pi bonding, which means these bonds in black are simply sp bonds. Looking at this carbon now, you'll see we have two pi bonds, one on either side. This carbon has two double bonds. This is a rare structure you will not see often, but it's a good question to sort of test your understanding of certain topics. This is called an allene. An allene, you won't see it often, but it does show up once in a while. If you're looking to draw a bond line structure of an allene, what you do is you draw two double bonds in a straight line because it's linear geometry, and you draw a little dot in the middle. That's how you might see an allene. This is the bond line structure of this right above here. This is the most basic allene you could draw. Again, that's a very rare structure, so don't worry about that. But as long as conceptually it makes sense that this allene is sp hybridized, then you're in good shape. This central carbon has two pi bonds, which means it has sp hybridization. Two of those three p orbitals are in pi bonding, so therefore all we're left with is an s and a p, which gives us sp. Okay. Linear carbons will be sp hybridized. Trigonal planar carbons will be sp2 hybridized. Tetrahedral or trigonal pyramidal carbons will be sp3 hybridized. Okay. So hopefully now you can see the connection between molecular geometry and hybridization state. And it will come into play in future chapters. So make sure you don't forget about all of this fundamental information. Okay, so let's first start off by counting the total number of pi and sigma bonds, because it will actually be easier to count the bonds in Lewis structure since every single bond is written out. Okay, so let's go through and maybe we will highlight in red all the pi bonds. and we will leave the sigma bonds as just black bonds. Okay, so remember pi bonds are going to be either double bonds or triple bonds, right? We'll have in a double bond, there's one sigma bond and one pi bond. And in a triple bond, there's one sigma bond and two pi bonds. So since we have one double bond and one triple bond, our total number of pi bonds is 3. And our total number of sigma bonds, we can count up here all the single bonds that we see. We have, I'll actually do it in blue so we can see a contrast to the ones that we count. So let's start on the left here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so we have 16 sigma bonds, 3 pi bonds, and then we're asked to show the geometry and hybridization of each carbon. So let's go through here. Our first carbon right here has 4 single bonds, and we know if carbon is connected to 4 things, 4 single bonds, it's going to be sp3 hybridized. And the geometry, 4 things spreading out around an atom, 4 single bonds, that gives tetrahedral geometry. Okay, and then the next carbon here, actually both of these carbons will have the same since they're both C's with double bonds and then 2 single bonds. Okay, so this carbon on the left of the double bond and this carbon on the right of the double bond, they both have a double bond and 2 single bonds. So if we recall, that should be sp2 hybridized. And both of these carbons are connected to how many things? 1, 2, 3 different things. They have 3 substituents. How do 3 substituents spread out around an atom? In a plane and 120 degrees apart. So trigonal planar. Okay, sp2 hybridized, trigonal planar for those two. Then we come to the triple bond. Both of these carbons have the same geometry and hybridization. Carbon with a triple bond and a single bond will be sp hybridized. And these two carbons are both connected to only 2 substituents. They have 2 substituents connected to them. So how do we spread 2 things out around a single atom? Well, they spread out in a linear fashion, 180 degrees apart, to get as far away as possible, which would be linear geometry. And then the final carbon, again, just like the first one, connected to 4 things, single bonds, sp3 hybridized, and tetrahedral. Okay, so there's the hybridization and geometry for all the carbons. And then the last thing we're asked to do is to draw the bond line structure. Okay, so let's do that over here. So I'm going to start with the triple bond to give us sort of a starting point to work from. Let's build out to the right side first of the triple bond. So this triple bond is connected to another carbon. Remember, those triple bonds are linear, so that's why I'm drawing these 2 carbons, all 3 of these carbons in a straight line, because these carbons in the triple bond are linear. Okay, so we have a carbon out here, and this carbon is connected to what? NH2. So I'm just putting this little vertice here. So at that vertice, we have our CH2. And then going out to the other direction, we have a carbon, another carbon, and then a third carbon. We have 1, 2, 3 extra carbons past the triple bond. 1, 2, 3 vertices in our zigzag. There's a double bond between the first and the second of those 3 carbons. And then on the very last carbon, we have an OH. So we'll add that OH to the last carbon, and there's our bond line structure. Okay, now for this structure, for this problem, we're going to sort of work in the opposite direction. Let's start with a bond line structure and make sure we can draw a Lewis structure from it. So we have here a couple, more complicated molecules than what we've seen recently, but this will be sort of a fun challenge to see if we can draw a Lewis structure from these bond line structures. So I drew here the 2 structures for 2 common medicines, aspirin, acetyl salicylic acid, and then Tylenol, which is acetaminophen. Okay, so these are the molecular structures for these 2 medicines. So taking the bond line structures, let's convert them to Lewis structures. We'll start up top with aspirin, acetyl salicylic acid. Let's draw first the 6-membered ring. This is a very common 6-membered ring. I'm actually going to draw these way over here just so we have more space. Okay, so let's start with that 6-membered ring in aspirin. This is a very common 6-membered ring that you'll see moving forward. So it's a hexagon, it has 6 sides, and you'll get used to drawing hexagons once you do a few. I like to start with a triangular top, triangular bottom, and then you just connect the 2 sides with 2 vertical lines. I think that's the easiest way to draw a hexagon. Okay, so we'll start with that 6-membered ring. We have 3 double bonds in the ring, alternating. Okay. This carbon up here is connected to an oxygen, which is connected to another carbon, which is connected to a CH3. And this carbon here has a double bonded oxygen on it. And then we'll put in the lone pairs at the end. And then up top on this carbon here, that's connected to another carbon, which is connected to an oxygen and a hydrogen, an alcohol. And then it's double bonded to an oxygen as well. Okay, so there's our Lewis structure. Now let's fill in with lone pairs. This oxygen on the bottom should have 2 lone pairs. Oxygen should have 2 lone pairs and 2 bonds when it's neutral. Up here, 2 lone pairs, 2 lone pairs. So we're adding 2 lone pairs to all those oxygens. Okay, make sure you don't forget about those. So there's the full Lewis structure for aspirin or acetyl salicylic acid. And now let's do Tylenol. We'll start with that 6-membered ring once again. I'm going to make a triangular shape. 2 straight lines down, and then another triangle. Okay, there's our 6-membered ring with alternating double bonds. Lower left here, we have an oxygen connected to a hydrogen. Let's throw in those lone pairs right now while we're there. And on the exact opposite side, we have N connected to a carbon, connected to a CH3. And that carbon has also a C double bond O. Let's throw in oxygen's lone pair. The nitrogen has a hydrogen, and the nitrogen should have 1 lone pair as well. So there's the Lewis structure for Tylenol or acetaminophen. Again, oxygen should have 2 lone pairs, nitrogen should have 1 lone pair. Okay. So if you're not comfortable with bond line structures by now, if this problem wasn't simple for you, then that's something you should definitely focus on, because we will be using bond line structures more frequently, almost exclusively from here on out. Okay, so it's very important to be comfortable with bond line structures. Okay, so for this question here, let's add, okay. So for this question here, we have this molecule. This is diazepam. This is a common medication for a number of ailments. And as we can see, it's quite a complicated structure. But what we're going to do is we're going to look at it and answer a few different questions on it. First, we're going to find out where all the implicit hydrogens are to make sure we know we can read the bond line structure well, and we understand not only where the carbons are, but where all those implicit hydrogens are. We'll count up all the atoms to give a molecular formula for diazepam. We'll show all the polar bonds with dipoles and charges. We'll identify the hybridization states of all the carbons, and then we'll identify the molecular geometry of both nitrogens. Okay, let's actually first start with, let's start with drawing the implicit hydrogens, and then we'll do the molecular formula right after that. Okay, so let's go ahead and start by drawing all the implicit hydrogens. Let's take red. So I'm just going to start over here on the left. This carbon right here is connected with 3 bonds shown in black. We have a double bond to the carbon up here, a single bond to the carbon down here, which means it needs 1 more bond in order to have 4 bonds. So there's 1 hydrogen there, there's 1 hydrogen there. All the way around this ring, we have carbons with a double bond and a single bond. So all the way around that ring, we just have carbons with 1 hydrogen. Okay. Remember, carbon should always have 4 bonds. If we look at this carbon right here, I'll put a dot. That carbon already has 4 bonds. We count up the black lines, 1, 2, 3, 4. It's double bonded on top with 2 single bonds, so there's no hydrogens there. Likewise, there's no hydrogens at this carbon. There's no hydrogens at this carbon either. And let's work our way around the other ring. This carbon has 1 hydrogen. Likewise, these carbons out here have 1 hydrogen. Okay, these all have 3 bonds, so they have 1 hydrogen in order to make 4. This carbon right here that I just put a dot on, that has 4 bonds already, so there's no hydrogens on that one. And then on the very end here, connected to the nitrogen, we have a CH3. So there's 3 hydrogens on that carbon. This carbon has 4 bonds already, and then this carbon down here has 2, which means we have 2 hydrogens on that carbon. So remember, all you're doing when you find out implicit hydrogens, you're just sort of looking at how many bonds carbon has and remembering that carbon should have 4 bonds total. So the difference is going to be the number of hydrogens that are implicit or undrawn when we have bond line structures. Okay. So with all these drawn up, let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so when we draw our molecular formula, we will have H13. How many carbons? Let's put green dots for all the carbons. Remember all the vertices of the lines, there's a carbon. So we have 1, 2, 3, 4, 5, 6 membered ring here. And we have another 6-membered ring over here. Then we have this carbon connecting the two. So there's 6, 12, 13, 14, 15, 16. Okay, so we have C16, H13, nitrogens, we have 2, we have an oxygen, and we have a chlorine. Okay, so there would be the molecular formula for diazepam, C16, H13, and 2OCl. I personally don't care the order. Typically you do CH and then you do your other atoms. I don't really care too much about the order of the other atoms, although some professors do have issues with orders and sometimes they like a specific order. But for me, I just put CH and then all the other atoms at the end in some order is fine. Okay, C16, H13, N2OCl. Okay, so we have the implicit hydrogens, we have the formula. Let's show the polar bonds with dipoles and partial charges. Okay, this might get a little messy over here. Let me erase some. Okay, so I redrew the structure here just to clean it up a bit as we move on. So we did the first one, we did the second one. Now let's show the polar bonds with dipoles and partial charges. Okay. So let's start up top. We have a carbon connected to a chlorine. Okay, so that's a polar bond because there's a large electronegativity difference between the carbon and the chlorine. So we're going to draw a dipole arrow pointing towards chlorine, which will give the chlorine partial negative and the carbon at the bottom partially positive. Those electrons are being pulled towards chlorine because it's more electronegative. Chlorine's partially negative, the carbon partially positive. What other polar bonds do we have? The CN bond. So we have a dipole towards nitrogen in both directions here from those carbons, making those carbons partially positive, and the nitrogen here partially negative. The C double bond O, of course, we have a dipole towards oxygen, making the oxygen partially negative and the carbon partially positive. And on this nitrogen, we have dipoles in every direction towards it. Again, this carbon is partially positive here, this carbon is partially positive here, and this is partially positive here. This nitrogen pulling electrons towards it, partially negative. Okay, so I'll draw over here just so everyone remembers. Up top, we have a carbon connected to a chlorine. So the chlorine is going to be pulling electron density towards it, making the chlorine partially negative, the carbon partially positive. And the same goes for the CN bond as well as the CO bond. Okay. We'll have a dipole arrow towards the right in all of these cases, towards the more electronegative atom, making the carbons on the left partially positive and the atoms on the right partially negative. Not a full negative, not a full positive, just partially. Okay. Those partial charges will come into play once we start doing chemical reactions. Okay. But for now, we just want to be able to identify where those partial charges are. Okay, there's that one. Identify the hybridization of all the carbons. Okay, whoops. Okay, so let's identify the hybridization state of these carbons. Let me clean this up a little bit. So we should remember if we have carbon with 4 single bonds, that is going to be sp3 hybridized. If we have, I'll draw that up here. If we have carbon with 4 single bonds, sp3. If we have carbon with a double bond and 2 single bonds, that's going to be sp2. And if we have a carbon with a triple bond or 2 pi bonds, that's sp. Let's color code these. That's what I like to do here, just to make it nice and clean. Let's put red on all of our sp3 carbons. How many carbons do we have here that are sp3? Well, there's this little guy on the end, the methyl group, the CH3. We also have this carbon right here is sp3 hybridized because it has only single bonds. It's a carbon connected to a nitrogen, a carbon, and 2 hydrogens. So this is going to be sp3 hybridized there. Now, looking around, all the other carbons have some sort of double bond attached to them. So let's get out blue for those sp2 carbons. We have double bonds all the way around these ring systems. These are called benzene rings. When we have a 6-membered ring with alternating double bonds, and we will be very familiar with them as we go throughout the course. It's a very common moiety. Okay, so all of these carbons with double bonds in the ring, these are all sp2. This carbon here has a double bond on it, 2 single bonds, so that's sp2. And our final carbon here has a C double bond O, and then 2 single bonds. So this is also sp2 hybridized. Remember, sp3 is the normal state for carbon. It has 4 single bonds. When we go to sp2, one of those p orbitals is participating in making a pi bond. So that means we only have 2 p orbitals. So it's sp2 hybridized. And when we have a triple bond, we have 2 pi bonds. So 2 of those p orbitals are responsible for pi bonding, which means we only have 1 p orbital left, which gives us sp hybridization. And we don't have any sp hybridized carbons here, so we don't have to worry about that. Just sp3 and sp2. And finally, it says identify the molecular geometry on both nitrogens. Okay, so we have 2 nitrogens here. I'm going to draw them out here a little bigger. So we have a double bond to a nitrogen, lone pair here, and then a single bond off to here. Put some squiggly lines. Again, just showing that it's connected to something else. We're not going to draw it. Okay, so this nitrogen on the left here, it has a double bond, it has a single bond, and it has a lone pair. Okay, so what's the molecular geometry for this? So let's draw it out. We have a nitrogen connected to how many things? That's always the first thing I like to think about, is how many things are we connected to? Well, we have a lone pair, we have a single bond, and we have a double bond. So I'm going to spread those 3 things out evenly around this nitrogen. If we have 3 things to spread out, it means we do it in one plane at 120 degrees apart, trigonal planar. But when we consider the molecular geometry, remember, we ignore the lone pair. So if we only look at the bonds on this nitrogen, it looks like it's what shape? It is bent. It has bent molecular geometry. Okay. Now, the last time we saw bent, we saw it on water molecule, where we had tetrahedral geometry, right? We had 2 lone pairs and 2 bonds. But you can also have bent when it's trigonal planar. Okay. If you have 1 lone pair and 2 bonds, then you can also get this bent shape, right? Because again, we're ignoring the lone pairs. So whether there's 1 lone pair on top, 2 lone pairs on top, doesn't quite matter. Okay, you can still get bent conformation if you have 2 bonds in this orientation. Okay, so that's the molecular geometry for that nitrogen. And for the other nitrogen, I'll draw here. what do we have? We have nitrogen, single bonded over here, single bonded, and a lone pair. Okay, so I'm going to draw that like we're used to. I'm going to spread out. We have 4 things, 1, 2, 3, 4. So I'm going to spread those out evenly in the shape of a tetrahedron. I'm going to put the lone pair on top. And we have this thing connected to, it's 3 carbons in each case. I'll just put C, C, C. This nitrogen is connected to 3 carbons here with 1 lone pair. So the electron geometry, everything's spread out in the shape of a tetrahedron. But when we consider the molecular geometry, we ignore the lone pair. So we are going to call this trigonal pyramidal. Trigonal pyramidal nitrogen. Okay, so there's the geometry for the nitrogens, hybridization, polar bonds with dipoles, implicit hydrogens, molecular formula. So this was a great question, sort of summarizing most of the work we've done up to this point. Okay, let's answer a few questions regarding polarity and wrap up workshop 2. Okay, so we have 2 final questions here regarding polarity and intermolecular forces that we can think about. So this question asks, which has a larger dipole between these 2 molecules and why? Okay, so let's start by drawing these molecules 3-dimensionally so we can get an idea of what's going on here. And let's draw some dipole arrows. So we have a carbon, CHCl3. We have a carbon connected to these 4 things, 3 chlorines and a hydrogen. So if we have 4 things, we're going to spread them out in the shape of a tetrahedron. Okay, like a triangular prism, remember, like a pyramid. So we have, doesn't matter where you put the substituents, remember, because molecules are free to rotate and move through free space. So let's put hydrogen and 3 chlorines, 1, 2, 3. And we should remember that we're going to have a dipole pointing towards chlorine. So we have a dipole pointing towards chlorine in every direction there, those 3 directions. But the CH bond, that's nonpolar. That's a nonpolar bond, nonpolar covalent. So there's no major dipole there for us to worry about. So we have these 3 dipoles for CHCl3. So the overall dipole in red is going to sort of be out in this direction, right? Sort of summarizing, sort of summing these 3 vectors of polarity, sort of pointing out in that direction, right? If you think about a triangular pyramid, we could draw it like this. If we put a triangular pyramid here, and we had 3 chlorines coming out at the bottom and a hydrogen on top, maybe it would be easier to see it like this. You have the 3 dipoles coming out towards chlorine. So the overall dipole would sort of be straight down the pyramid. If this was a pyramid here, the dipole would be sort of pointing straight down through the floor from the center, from the carbon here, straight down through the floor of this pyramid, right? In between all these chlorines, Again, it's hard to represent on a 2-dimensional surface, but as long as you understand the general dipole direction is obviously towards the chlorines, we're in good shape. So let's compare this to CBr-Cl3. Let's draw that here. Let's draw it the same way so that we can compare more clearly. Let's draw the 3 chlorines there and then draw our different atom in the same spot. So again, we have dipoles towards the chlorines in each direction. And now we also have a dipole towards bromine. So we now have a dipole sort of in the opposite direction as our overall dipole in the previous one. So this arrow, this dipole pulling towards bromine is actually sort of canceling out these other dipoles, right? See the difference? We have a hydrogen on the left, we have a bromine on the right. So this bromine is working against our overall dipole, which means that the overall dipole is going to be much weaker on the right, right? It's almost going to be no dipole whatsoever, because we know if we look at CCl4, carbon connected to 4 chlorines, that has no dipole, it has no overall dipole, because all the chlorines are pulling electron density equal and opposite from that carbon. So the overall dipole is actually 0. A very similar thing is going on here because bromine and chlorine have very similar electronegativities. So the overall dipole for this is actually very weak, almost none. Okay, so that means which molecule would have the larger dipole? Well, it would be CHCl3. Okay, so why does CHCl3 have a larger dipole? Well, because if we had a bromine, right, if we look at the right here, if we have a bromine attached to that carbon, then we have dipoles sort of in equal and opposite directions all over that carbon. Remember, those 4 substituents on the carbon atom are spread out in equal and opposite directions in the shape of a tetrahedron. And so if electron density is being pulled away from that carbon in every direction, the overall dipole is pretty much 0. If we have a CH bond in the mix, right, if we have CH bond, there's no dipole there, which gives us an imbalance in polarity, which gives us an overall dipole. Okay, so that would be a very acceptable answer. That would be what I would write. So our molecule with the larger dipole is CHCl3. Okay. Now for our final question here, let's order these 4 molecules by increasing boiling point 1 through 4. Okay, so we have a 4-carbon chain, butane. We have a 4-carbon chain with an alcohol, butanol. We have a 4-carbon chain all connected to a central carbon. This is called T-butane. And then we have diethyl ether right here. This is a very common solvent, diethyl ether. Okay, so looking at these, which one is going to be our lowest boiling point? Well, it's going to be one of our hydrocarbons, either this or this, right? The alcohols will have a higher boiling point because they're going to have a dipole or hydrogen bonding. And remember, the dipoles and the hydrogen bonding are much stronger intermolecular forces than our London dispersion forces or our fleeting dipole. And hydrocarbons, like these 2 that are shown here, only have fleeting dipoles. So let's compare butane in the straight form here to T-butane. Okay, so comparing these 2, we have a straight chain and we have branching. Now, hopefully we remember that if we have a straight chain, I'm just drawing a larger molecule over here. If we have a straight chain of something versus something that is heavily branched, the heavily branched molecule has smaller surface area as opposed to the long chain. This long chain here has bigger surface area. It's more spread out. So if we have the molecule more spread out, that means the electrons all over that molecule, in and around those atoms, are more able to freely move and can create some fleeting dipole interactions. Okay, so a larger surface area will produce larger fleeting dipoles. So our lowest boiler is going to be the branched hydrocarbon on the bottom here. So let's put 1 right there, followed by our straight chain 2. Again, because we're first eliminating the oxygen compounds because those will have much higher boiling points due to dipole interactions. So comparing our 2 hydrocarbons here, we're comparing a straight chain versus a branched, and a branched hydrocarbon will have a lower boiling point because it has less surface area, which produces less fleeting dipole interactions. Okay, and then we have two. Now let's consider our two oxygen-containing compounds. Now, both of these compounds have dipoles, right? They both have dipoles towards oxygen. So we could get some dipole interactions, but the alcohol on top has a OH bond, and that should cue you to think hydrogen bonding. Hydrogen bonding is the strongest intermolecular force that we'll consider, and it really keeps things stuck together really well. Remember, it's responsible for a lot of the shape in our DNA. It's responsible for water having a remarkably high boiling point for its structure. Okay, so OH bonds and NH bonds are very strong in terms of intermolecular forces. That hydrogen bonding is very strong. So if we're comparing an ether, an oxygen with carbon bonds, versus an alcohol, an OH, the alcohol will have the higher boiling point, all other things equal, because we're comparing essentially dipole interactions to hydrogen bonding. And hydrogen bonding is our strongest intermolecular force. This ether here, 3, doesn't have any hydrogen bonding. It doesn't have any OH bonds. It only has a dipole towards oxygen here, towards oxygen here. Now this will increase the intermolecular forces. It increases the molecular stickiness, but OH bonds, NH bonds are just much stronger, okay? So our lowest boiler will be this T-butane, followed by 2-butane, followed by diethyl ether, followed by 4-butanol. Okay, and again, we'll get more into nomenclature as we go. But hopefully the concepts make sense in terms of intermolecular forces. Remember, we have our fleeting dipoles, we have our dipoles, and we have our hydrogen bonding. So those are 3 forces you should definitely be aware of and be able to understand and manipulate on an exam. Okay, so that's everything I have for workshop number 2. I hope that was helpful, and I will see you in the next lecture.